Swayam Prabha. Digital India. Educated India.
In the last class, we discussed about basics of instrumentation. Today, we will be focusing mostly on the actual sensors and transducers which are used for condition based maintenance. And of course, this list is pretty exhaustive, but we will be focusing mostly on the transducers which are commonly used mostly for vibration monitoring, current monitoring, temperature detection, etc. Well, to briefly discuss in a nutshell, the transducers which are used in CBM are for vibration. Usually the accelerometers are used. So, whatever you see within the parenthesis in the slide are actually the name of the transducers. So, the mechanical parameter vibration is used by is measured by accelerometers. The noise or sound which we hear or machineries radiate is measured usually by a microphone. This both the accelerometers and microphone could also be used to measure the noise underwater when you are talking about a propeller noise inside the sea, and in that case those are known as hydrophones other than microphones. Similarly, if you want to measure the vibration of a offshore structure which is submerged in the water, you could use perhaps underwater accelerometers. Now, we will discuss about them later on. But another very important parameter in mechanical machines, as you would have seen in signal processing, is related to the rotational speed, because as I was telling you, a machine needs to operate, and particularly you will see that in many of these machines the most common element is a shaft which is rotating and held on a couple of bearings. So, the rotational speed of the shaft may change, may fluctuate with time because of load, because of defects. So, the instantaneous measurement of rotational speed at all times is very, very important. We would have studied in our undergraduate instrumentation courses that we use a tachometer to press on a shaft, and then use a mechanical tachometer to measure the rotational speed. But in a remotely operating machines where there are no persons, I possibly cannot have anybody stick in a tachometer, mechanical tachometer to a rotating shaft. So, we have to think of optical ways or the key trigger like the key phaser, which are used to measure the rotational speed. Another important aspect which we need to measure is the motor current signature analysis. So, current needs to be measured. Current we use, we have used ammeters to measure the RMS current, but current waveform has to be measured. You could be using what is known as an Hall effect sensor, we will discuss that. And then next comes temperature. Temperatures, I do not mean temperature of a human being here, but temperature of machineries, temperature of bearings, temperature of oil baths in the gearboxes, and these temperatures could be very high. I mean, imagine temperature of a blast furnace. Inside a blast furnace, I possibly cannot stick in a thermometer to measure the temperature of a blast furnace. So, we have to use certain non-contacting type sensors like the infrared or the pyrometers, and certain high temperature, high range of temperature which could be measured, or perhaps the thermocouples or the RTDs, resistance temperature detectors. And then in many of the process parameters, particularly in chemical plants, wherein people need to measure the flow rates of certain fluids or slurries. Okay. And how do you measure such flow rates? In the lab, we all have used venturimeters, rotameters, pitot tubes, etc., orifices to measure the flow rates. But then you would have seen where there you need to measure the pressure difference. From pressure difference you need to calculate the flow rates, you need to know the area of the pipe and so on. But turbine flow meter is another device which could be very easily put online on a pipeline, and then all you will be getting is a certain speed at which the fluid is flowing through it, and once you know the area of the pipeline, if you multiply that, you will get the flow rate instantaneously. So, when the processes are very dynamic, when the flow rates are changing because of the operations on the plant, particularly in large oil refineries and chemical plants, that is where we use turbine flow meters. And another very important NDT, non-destructive test technique, is the measurement of the thickness. Now, as I was telling you, there is a pipeline. Because of the fluid flowing through the pipeline, what happens? Deposits get deposited in the inner wall of the pipeline. So, that is going to affect the flow rates. So, such scale formation or deposits will reduce the internal thickness of the pipe. So, from outside, how do I know that such a buildup has occurred in the inner walls of the pipeline? This could be very easily measured online by an ultrasonic thickness gauge. Sometimes people even do a portable X-ray radiography of the tube from the outside, particularly in boiler tubes, when there is a lot of scale formation because of the water flowing through the pipelines. There is scale deposits and the thicknesses get reduced because of rather thicknesses increase. So, the effective diameter of the pipeline for flow reduces, and this can be measured by techniques like radiography or ultrasonic thickness gauge. And another important applications of ultrasonic thickness gauge, which I had told earlier also, suppose there are internal cracks in the structure which cannot be seen visibly from the outside. So, if we have an ultrasonic probe, it can be used to measure the presence of the crack. So, I will begin one by one. To begin with, let me tell you what this accelerometer is about. This is just a piezoelectric accelerometer. We had studied the basic of accelerometers in the lecture on vibrations. Essentially, what happens is, let me tell you the internal mechanism here. I have a mass here, so essentially if this is put on a structure which is having a motion x, okay. So, onto this I put an unit like this. So, I would like to measure the motion x. Now, what happens because of this motion x, this mass is going to have a motion y, it dependent on the k and c. So, somehow if I can have this motion y related to x, okay, with certain functions of k and c. So, indirectly if I measure y, I can know what the x is, and this x is actually the vibration displacement here, and this I will put it in a nice housing, okay, wherein, so this is actually your sealed unit or casing. Okay. Now, because this mass is having a motion y, I could be putting certain sensing element. Okay. Now, what could be the sensing element? The sensing element could be, as I have told you, could be strain gauges, because of this motion there will be some strain, and the strain will be indirectly responsible, get a measure of what x is. So, this is what initially was the strain gauge type of accelerometers, but now strain gauges need certain power supply, they need to know resistance, they have to be, resistance should not change with temperature. So, there are certain problems with this kind of accelerometers, but then came a material which is known as piezoelectric material. Now, piezoelectrics are actually naturally occurring materials. If you have not seen a piezoelectric material, I do not know if you have seen sheets of mica. They look kind of mica sheets, and they occur in nature, though artificially also we can create them in the laboratory. I will come to that later on. But these piezoelectric crystals which are found in nature have a certain property, that is, given a force or a motion, they are going to develop a charge. I will put a generic motion charge, and it is in a particular direction. So, they give the highest amount of charge when loaded, unloaded in a particular direction. So, that is the most sensitive axis of this piezoelectric crystals. So, they are isotropic, they have a directional feature. So, if I go back to this mass here, if I put a piezoelectric crystal next to this mass or embedded it in this mass, so that it is sensitive to the motion in the x direction, then as soon as I have a motion x here, this piezoelectric crystal here is going to have a motion and it is going to produce a charge. Okay. So, because of the feature of the piezoelectric crystal, if there is a motion in the horizontal direction, it is not going to sense, because once this unit, if I put on a structure, it may so happen that I am only measuring in x direction, but what if there is a strong motion in the y direction, in the z direction? Is my piezoelectric crystal going to sense it? No, and that is the advantage of piezoelectric crystal. It is very directional. Okay. So, the manufacturers find out which is the most sensitive direction of the piezoelectric crystal, and they align it in the direction of measurement of the acceleration or the motion, because as I was telling you, vibration is measured in any direction. I need to specify the direction. For example, when I have an vibration transducer put on a bearing of a shaft, so this is the radial direction, this is the along the horizontal direction, this is the axial, and this is the horizontal, or this is known as the vertical. So, if I put an accelerometer on the bearing housing here, so it is sensing in only the vertical direction. If I want to measure in the axial direction, I have to rotate it by 90 degree. So, that this becomes in this direction. So, I have to align the accelerometers along their most sensitive direction. So, coming back to the discussion of piezoelectric crystals. So, piezoelectric crystals are found in nature and which have this property that whenever I give a motion, they give a charge. Another very important feature of the piezoelectric crystal is, given an electrical charge, they are also going to have a motion, and that is what is used in what is known as, we are talking about in particularly in control, when you talk about smart structures. Just for an example, say I have a cantilever beam. Okay, in its first mode of vibration, it will have a mode shape like this. Okay. Now, suppose I want to reduce, it is having a motion. Suppose I want to reduce this motion here. So, what I could do is, I could perhaps bond certain piezoelectric material and give an electric charge, a proportional electrical charge here, so that this comes back. Okay. So, particularly whenever because of motion there are certain uncontrollable flutters. Okay. Flutter means an uncontrolled vibration, low frequency low amplitude vibrations, and I could reduce that by putting up piezoelectric crystals. For example, when you have a space shuttle, when you have the solar panels deployed out of a space shuttle, because of motion they will have some amount of motion. So, this motion could be reduced by putting in piezoelectric crystals and giving them proportional charge, so that they will give a motion back and they will go back and reduce the motion. So, this is we are not going to discuss this in the transducers or CBM, but it suffices to say that in accelerometers nowadays we use piezoelectric crystals as the most sensing elements, because they can withstand high temperature, they do not require an external power supply like in the case of a strain gauge, and they can be very small in size, okay, and then they can be also put inside. So, for example, if you look at this accelerometer here, this is the connector wherein we get the signals to we get the charge, and which will be amplified and then propagated. So, this transducer, this is the base, and the piezoelectric crystal is already sealed inside this. Okay. I will show you another accelerometer. This is another accelerometer where this diameter is about the size of a 50 paisa coin, okay, and there is a connector wherein we connect the cable, and sometimes the connector is on the top, sometimes it could be on the side, it depends on the convenience of using it. Now, this is a very important accelerometers, because, and this is known as a triaxial accelerometer. If you see here, it is written X, Y, Z, and these studs are used to either mount them to the structure where we are measuring the vibration. So, X means the cable connected out of this location is measuring the motion in the x direction. Z means it is out of the plane of this presentation here, and Y is in this direction. Okay. So, you can think of it that 3 piezoelectric crystals having mutually perpendicular orientations have been put together, so that at one point I can measure the vibration in 3 directions. Okay. So, this is very convenient that I need not put 3 uniaxial accelerometers, rather at one place I put a triaxial accelerometer, and sometimes in short it is known as a triax, people loosely call it as triax. So, the output which comes out of the displacement, you will see from the equations of vibration that the y can be actually proportional to x double dot, and then we will get a measure of the acceleration of the base to which this transducer is attached. Now, sometimes we need to know what the velocity or what the displacement at that measured point is. If you will recall, suppose I will have a motion in general terms, x is equal to a sin omega t at any frequency. This is the expression for the displacement. So, x dot is the velocity, is nothing but a omega cosine omega t, and x double dot, the acceleration will be minus a omega square sin omega t. So, if I am measuring the acceleration amplitude, I know my a omega square is nothing but the acceleration amplitude, which has been measured by an accelerometer. And if I plot the spectrum from the signal which is obtained out of the acceleration accelerometer amplitude, I may get something like this, right. So, this is equal to omega by 2 pi. So, such a spectrum you can very easily obtain by doing frequency analysis or Fourier analysis of the vibration signal which you have measured from the transducer. Now, if somebody wants, well, tell me the velocity spectrum of this signal, you could do it very easily, or the fact that once you divide this by omega, you will get the velocity spectrum, isn't it? And then if you divide it by a omega square by omega square, you can get the displacement spectrum. So, this is done electronically. Once you measure with an accelerometer, you measure the acceleration a omega square. Once you do the Fourier analysis, you will get the spectrum. All you have to do is at every frequency, either you divide it by omega or divide it by omega square, and then you will get the velocity spectrum or displacement spectrum. And so, this is done as a post processing. Many vibration meters, essentially a vibration meter is nothing but an accelerometer with its signal conditioning amplifier and a readout is what is a vibration meter. And the vibration meter, you will have an option either to see the velocity spectrum, displacement spectrum or acceleration spectrum. I will show you a typical vibration meter now which is available nowadays. In this vibration meter, of course, the reason this is pointed like this is this also has an option that this electronics could be also used as a sound level meter, wherein if you replace this end by a microphone, this becomes a sound level meter. Otherwise, since we are using it as a vibration meter, there is nothing here, just a dummy cap here. All you have to do is with a cable attach your accelerometer into this. Okay. So, all the electronics in terms of the signal conditioning is here, and on this screen you could see the spectrum of the vibration or the velocity or the displacement. You could put a filter, so that if you say I am only interested to know the vibration at 100 from 100 to 1000 hertz, you can very well do that, and this will display you the overall vibration level in the meter. Okay. But before we had this vibration, this is a digital vibration meter which is pretty recent, and this we have just acquired in our lab. But then if you go to the earlier days, we had this analog vibration meter, and this is what it looked like. So, this is the accelerometer which I was just talking about. This is an uniaxial accelerometer. So, the piezoelectric crystal is inside this, okay, and this can withstand very, very high temperatures, may as well go up to about 200 degrees Celsius or 300 degrees Celsius. This is shielded from moisture, humidity, rain, etc. And then this cable, because as soon as the charge is produced, we will go to the details of the vibration transducers regarding the mounting, etc. in the subsequent classes. But all it suffices to say is a charge is produced, and this charge goes into an amplifier wherein the charge is converted to voltage. So, once I have a voltage signal corresponding to the acceleration, all I can do in this meter here, in this vibration meter, there are options whether you want to see the analog displacement, analog velocity, because there are analog filtering units. This is not a digital device, but the example or the device I showed you before, this is a digital device. So, there is an A to D converter. Once we have digital, we will get the velocity and displacement very easily just by dividing by omega square and omega. But in those days, when the computer aided data acquisition was not available, people were using electronic integrators, or in this case, electronic integrators to obtain the displacement and velocity from the measured acceleration. Okay. And then you had an analog readout. So, this is kind of very obsolete, but this was a very popular equipment of a particular manufacturer. Okay. Now, before I conclude my discussions on the vibration measuring transducer, which is an accelerometer, we will discuss about the details of how the vibration accelerometers have to be mounted on structures and so on later on. But it suffices to say right now is this: vibration accelerometers have very good frequency response. This is a typical frequency response curve of a vibration accelerometer, and this sensitivity, take it back again. So, there are two important parameters, one is the dynamic range and another is the frequency range. Because we are talking about dynamic signals. So, the accelerometers have a very large frequency range, and the smaller the accelerometer, greater is its frequency range, and bigger the accelerometer, greater is its sensitivity and maybe dynamic range. Typically, the sensitivity of these accelerometers are maybe 10 meters per second square per picocoulomb. Okay. So, this is the acceleration to the or let me put it this way, 10 millivolts to picocoulomb, and this will be converted to picocoulombs to millivolts to meter per second square, and then we will have another conversion, picocoulombs to meter per second square, and then finally, we will get millivolt to meter per second square. Typically, the frequency the sensitivity ranges of these accelerometers are about 1 to 100 millivolts per meter per second square. Okay. Now, question is, the piezoelectric crystals produce a charge. So, I cannot store charge for a long time because they will discharge and decay with time. So, a charge to voltage conversion needs to be done, and once I have the voltage, I can send it through the signal. So, some accelerometers which we just discussed, they are the charge type. Another is the integrated charge type. Here the output from this is a charge, here from the output from this is a voltage, because the voltage conversion is done inside this. So, there is an additional electronics built into this kind of accelerometers, because straight away I am getting a voltage. Now, this additional electronics are basically IC chips. So, because they are inside this element which is put in a stainless steel casing, I cannot subject this integrated charge type of accelerometers to more than 100 degrees Celsius is not allowed. Okay. They have to be at a lesser than 100 degrees Celsius. But this charge type, because the electronics is outside in the vibration meter, I can go maybe up to 250 degrees Celsius. Okay. So, this is two things you have to keep in mind, particularly when you are doing vibration monitoring of places where the temperatures are high gearbox temperatures or bearing temperatures. We have to use charge type of accelerometers, and this integrated charge type of accelerometers or ICP type of accelerometers could be used in room environment when you are doing modal testing, when you are doing in low temperatures, you can use this kind of accelerometers. But for high temperatures, for rugged industrial accelerometers, which you need to always use charge type. So, this selection you have to keep in mind when you are using accelerometers. Now, let us talk about another important mechanical parameter is this mechanical noise, and this is essentially measured with a microphone. So, microphone, as I was telling you, has two plates. So, one is the base plate and another is a very thin membrane or a diaphragm. So, this membrane is going to deflect and this gap is going to change. And this gap to begin with could be about 0.002 centimeter. So, you can imagine the care they take in manufacturing this piezoelectric microphones. Okay. And this microphones could be of many type. One is, this is what I have drawn here is a condenser microphone. What I am showing here is a piezoelectric microphone. The question is, they look very similar from the outside. Okay. And this is a protective cover. So, this is the this slots here, below this slots is the diaphragm. Actually, this is a protective cover, and it is always advisable not to remove this protective cover. This is possibly the thinnest foil you can ever imagine. Okay. Even if you blow hard, you may sometimes damage the membrane. Okay. So, this is why it is a very sensitive equipment. So, we have to be very careful, and thus this is this protective cover which is advised not to be open. So, what happens, either be it condenser microphone or piezoelectric microphone, the only difference is that in the case of a condenser microphone, because of the deflection of the membrane here, this gap is going to change. So, the capacitance between these two plates is going to change. Thus, I will get a charge which is or voltage which is proportional to the motion of the diaphragm. That is what is the condenser microphone. Okay. But in a piezoelectric microphone, what we have connected to the base plate, we have certain piezoelectric crystals. So, because of this motion, the piezoelectric crystals will have a deformation, and then that is why they will have the output. Now, the difference between condenser microphone and piezoelectric microphone is condenser microphones can last forever practically, because there are just two metal plates. Okay. But the piezoelectric microphones will lose their sensitivity, because the piezoelectric crystals could possibly age, because they are exposed to the elements. In the case of the sealed accelerometers, the piezoelectric crystals were sealed forever. They were not open to the moisture or air and so on. But here in the case of piezoelectric microphones, they are exposed, because we have to have an opening for the air to be impinged on the membrane, for that it has to deflect. I cannot seal it totally. Since they are open, they will lose with their sensitivity with time. So, they may age. So, if a condenser microphone just if it costs 50,000 rupees, a piezoelectric microphone will cost perhaps about 10,000 rupees, just give you an order of magnitude. And in your high school physics, you must have talked about the carbon granule microphones, the voice call. So, where there is a, because the diaphragm moves, there is a movement of the diaphragm. So, the coil will move, and then a proportional voltage will come because of the movement of the diaphragm, where to which this coil is attached. So, if that microphone costs 100 rupees, piezoelectric will cost 10,000 rupees, and this will cost 50,000 rupees. So, you can imagine what kind of ranges we are talking about. So, these condenser microphones have very high dynamic range, at the same time very wide frequency response. They can measure as low as 0.1 hertz to as high as 100 kilohertz. Now, we only hear about 20 kilohertz, but there are many phenomena, the ultrasonic phenomena beyond 20 kilohertz, which can be monitored through such condenser microphones. And again, Similar to the observations in accelerometers, when the diaphragm diameter reduces, their natural frequency is high. So, the smaller the diameter, and this is about, as you can see, this is about half an inch here. So, this has a typical frequency range up to about 20 kilohertz. If I make it smaller, I will have accelerometers up to 70 kilohertz, up to 200 kilohertz, because you will be wondering, what do I do with 200 kilohertz, because I cannot hear any sound at 200 kilohertz. That is fine, but there are a lot of mechanical phenomena occurring at such high frequencies, particularly whilst you are doing abrasive jet machining, water jet machining, etc. They produce a lot of ultrasonic waves and which could be captured by such microphones. Similar to the vibration meter, these microphones are also put in a sound level meter. So, this is a sound level meter wherein the microphone is only this part, okay, and then we again have a preamplifier and a display unit which will give you the overall sound pressure level in a particular frequency range, and then you have an option of selecting the frequency band and so on, and also you have an option of either recording the output. Okay. So, this is a typical sound level meter. Now, this microphones could be used to measure noise underwater, and these are actually known as hydrophones. So, the piezoelectric sensing element is here, and this black one is just a protective cover. So, when the water waves or the waves come and impinge on this surface, the piezoelectric crystal inside this also gets a motion, and this signal is converted and sent to a charge amplifier. You will be wondering why such a long cable, because this is about 10 meters long cable. This could be ordered to even 1000 meters, 1000 meters, 1 kilometers. You want to measure your noise deep in the ocean, you can have an hydrophone just dropped into the ocean, and then you will have a long cable coming from that, and in the air on the ship you could be possibly instrumenting it to an amplifier and then see the output. Okay. And such are known as hydrophones. You could have an array of hydrophones to sense from which the direction the sound is coming, and particularly in ship hulls and submarines, in the front there is a lot of such hydrophones which actually work as sonars. Okay. And this is very costly. Now, when I was talking about the microphones, if the microphone is 50,000 rupees, this is about 3 lakhs of rupees. So, I am just giving a feel of the price of this equipment and how sensitive and important these things are. Similar to the hydrophones, we also have underwater piezoelectric accelerometers. Again, you see a long black cable, and this is the accelerometer, and which is again this end has to be just attached to the structure, and then you take the long cable and then go outside on the air or in the ship or in your lab, measure this using an amplifier. Okay. So, we just concluded measuring the I was talking about the vibration and noise measurements. Let me talk about the rotational speed measurements. Two important equipment are used to measure the rotational speed. So, one is the key phasor. What essentially you have is, you see this there is a coil inside it, okay, and then once the shaft is rotating, of course, I do not have a shaft here, the shaft is rotating because of the keyway, the gap between the keyway and this is going to reduce every revolution, right. So, because this gap is reducing, you will get a flux. So, you will get a spike. This will not give you absolute RPM, but measuring this on a time base, you can know what is the inverse of it is what is the rotational speed, or this could be used to trigger the occurrence of an event, and that is what is the key phasor. Okay. The next one is the phototach, wherein of course, you do not see the setup here, but this is a device wherein I give an optical light, okay, and on the shaft I can put a reflective tape, and every rotation this reflective tape is going to come just below the transmitted light. So, it is going to reflect it back again. So, I will get a light pulse back. So, again from the electronics I can measure the distance between the time distance between the transmitted and reflected, and know the time taken for one rotation. So, such phototacks, the beauty of such phototacks is, unlike mechanical tachometers wherein you have to press onto a shaft, and because of this such a load the shaft speed could reduce. These are not loading the structure and they have a very fast response time. You could measure speeds as high as 50,000 RPM with such phototacks or tachoprobes. Now, another transducer which you used is the Hall effect sensor. Now, to measure current, we all know that ammeters are used, but ammeters give us an RMS output, but I am interested to know the current waveform as a function of time. Okay. And this is given by a Hall effect sensor very easily. It happens here is this conductor, a conductor, and all I produce here is a magnetic field. Okay. I have a battery source, I produce a magnetic field, and then there is a current carrying conductor. So, depending on the intensity of the current, depending on this magnetic field, this guy is going to generate a voltage. Some of the simple laws of magnetism. Okay. And this current is proportional, is shown as an output voltage. So, usually the typical sensitivity of such Hall effect sensors is about 10 millivolts per ampere or about 100 millivolts per ampere. Okay. I can increase the sensitivity of this by, instead of one cable, let me suppose this is the ring and I produce a current carrying, and there is a certain magnetic field which is going around. To increase the sensitivity or output of this system, I could be putting in few more current carrying conductors. So, the output will increase, and I can always zero set it. The advantage of this is this has a good frequency response, almost from 0 to 500 hertz you can measure with such current carrying Hall effect sensor, which is not possible with ammeter. Now, our typical current, supply current is about 50 hertz, okay, and these ammeters can measure only up to 50 to 100 hertz. But you will see later on when you talk about motor current signature analysis, when we are discussing about how this waveform can be analyzed to find out the mechanical defects, I need to know the waveform, whether there is any fluctuations in the waveform, etc., at what frequencies. So, this is where this Hall effect sensors are very advantageous, and I will get a voltage output corresponding to the current carried by the conductor. And another mechanical parameter is the temperature. And temperatures could be measured by thermocouples, RTDs, pyrometers. Okay. Of course, nowadays the thermal imaging cameras are available. because there are many devices which will change color excuse me, which will change color based on the temperature, okay, the charge coupled devices, and then they will give a voltage output corresponding to the color, and which are used nowadays in the cameras, etc. So, these have been if you can focus beam into such cells, okay, and then they will give a voltage corresponding to the intensity and the color, we can get a indication of the temperature of the target. And you all recall the Stefan-Boltzmann law, okay, the T to the power, how it depends on the emissivity and the T to the power 4, okay, the heat flux. Okay. So, this is the absolute temperature of the body to the power 4 and the surface emissivity, and this has been used in thermal imaging cameras and pyrometers, but here I want to show you what we have is a thermocouple. Essentially a thermocouple, and if you will see here, thermocouple is nothing but when we have two wires kept at different junction, this could be copper, constant 10, it could be copper, iron, etc., copper, nickel. So, many such combinations are there, and based on these combinations they have different temperature ranges. So, such a junction, if it is kept at a temperature, I will get an EMF, okay, and this could be another T1, T2. I will not go into details of this, but suppose if this is at a known temperature, I know the voltage, I can look into the calibration tables and know the temperature. Other way, there are many ways of looking at it. I can have an electronic compensation because of this reference temperature, and then I will get a voltage corresponding to the properties, and this could be calibrated to display me the temperatures. So, this is just one end, because you would have studied the thermocouples means I need two ends. Where is the other end? The other end, which could be a ice bath or a boiling point bath, actually all I need to do is just the reference voltage. So, this could be given electronically, and this is what is given in such handheld temperature detectors, which is essentially an electronic unit, and this is the unit of target or the probe, which has actually two ends, which could be put to the place where you are going to measure the temperatures. And this is a handheld device. Nowadays, many data loggers are there, which will just record this voltage, and then you will get a record of the temperature signal. Particularly when you are talking about temperatures around an engine, wherein we need to know the inlet temperature, the exhaust temperature. So, we can put all around the engines a lot of these thermocouple sensors. In fact, nowadays if you look into any modern engine, you will see on the display in your car that the temperature of the engine is displayed, either it is hot and cold, but the detectors are RTDs or thermocouples. Okay. Whether the oil temperature is increasing, the water bath coolant temperature is increasing, etc. Such thermocouples are built around it. And then nowadays even in engines there are automatic diagnostic modules. So, I will talk about this when you talk about the case studies, but such modules always keep a log of the temperature of the important functions or systems in your vehicle engine, particularly the exhaust temperatures, the inlet temperatures, the oil temperature, the coolant temperature, and so on, and this is automatically logged into the data logger. So, if you and it always overrides, and once you go to the service station, if there is an abnormality, it will record in the data logger. So, nowadays if you take your car to your service station, they will hook up a data logger and retrieve the data from your car's engine, and then they will do a diagnostics, okay, because they know the past history of your vehicle, which is apparently ignorant to when we drive a car, but nowadays it has become mandatory in the abroad, and it has become mandatory in our country also to have a diagnostic modules to be placed on an engine, okay, wherein particularly now we are not in an engine, we are not particularly talking about vibration or noise, but mostly the temperature and pressure and so on. So, temperatures are measured while you are driving, it is apparent, not obvious to the driver, but these things do happen, and it gets stored in a simple memory module in the engine diagnostics module. Okay. And once you go to the service station, you will say sir, your thermostat is having a problem, you would have no clue how he came to that conclusion, but looking at the diagnostics, looking at the past data, he can see the abnormality and so on. Okay. So, technology has gone so far, we do not know about it yet. And this is the infrared temperature detector, okay, again which works on the principle of pyrometers. So, this we give an optical light beam, and depending on the reflected intensity back, we can know the temperature. All you have to do is, it is set for a particular emissivity, but there are very much sophisticated versions of this infrared temperature detector, wherein you can choose and select the emissivity. You can have an plot or a storage of the temperature automatically over a period of time, and then many places wherein we physically cannot go to measure the temperature. Okay. We can aim this at that surface. For example, in a blast furnace, say, see this blast furnace, in the inside they have a refractory lining. Okay, and then lot of very high operations are going. What happens when the blast furnace actually ages? Some of these refractory linings may weaken, may break off. So, if you from the outside, if you do a, if somebody is standing next to the blast furnace and does a thermal scanning, either through a thermal imaging camera or just an infrared temperature detector, he will see some spots wherein the temperature has suddenly increased, because the insulation, the refractory insulation, thermal insulation has deteriorated. We can easily record it. Okay. So, because CBM always does not mean of dynamic signals, but these give us some clue as to what could be possibly wrong with the system. Okay. For example, another place is, I have a pump or a motor driving a pump, and because of misalignment, this coupling is becoming hot. So, from a far off place, I could put a temperature detector and see the temperature of the coupling, temperature of the bearing, etc. So, I can do that. Okay. Another very important equipment is this ultrasonic thickness gauge, which I had discussed about it. You will see this is the ultrasonic probe, which has to be put onto a surface whose thickness or I need to measure. So, you will see here two signals. One is the transmitter, it will transmit the ultrasonic wave. So, once this wave reflects back is a receiver. Again, by knowing the time difference, you will know whether the, and because the speed of the ultrasonic wave in the medium is being set here, you know how much time it should take for a certain distance to cover. So, because if you are scanning this probe on the surface, and if there is a defect here, every time this is going to get incident reflected, but once it comes here, it is going to get incident and reflected. Okay, so in the ultrasonic thickness gauge, I need to measure this distance t. T is nothing but, or I will put it, this distance S is nothing but c times the time taken. C is the speed in this material, t is the time taken. So, in this probe there will be a constant time. So, by knowing this t, c is set by you can know what S is. So, this is the principle behind this ultrasonic thickness gauge, and because being high frequency waves are always very directional. So, they are directional, but this ultrasonic thickness gauge could be also used to detect crack, ultrasonic crack detectors in the vice versa. You will see how much time it took. For example, if you are scanning and suddenly you see the time between the crack decreased, that means there is a short distance this wave has gone. So, there is a defect, impedance mismatch, and that is the principle behind ultrasonic crack detectors. Okay. So, these were some of the equipment which we are going to use, or transducers which are going to use in CBM, and I just gave you a brief about these transducers, and we will discuss about them in detail when we go about the specific cases of vibration monitoring, noise monitoring, motor current monitoring, NDT, and so on. Okay. Thank you.